Hi everyone, hope you are doing fine. So today I am going to solve the path existence query in a graph 1 problem, and in the next video I am going to solve the second part of this problem, which is a harder one. So yeah, let's start with this problem. So in this problem we are given a integer we are given an integer and representing the number of nodes in a graph labeled from 0 to n minus 1, and also we are given an integer array nums of length n, like a sorted in a non-decreasing order, by non-decreasing order it means that is sorted in a increasing order. So yeah, and we are also given a undirected and but how we we have not given there is a edge between node u and a v. So they are saying in the problem that undirected edge exists between node I and j if there is a if the absolute difference between two node values, node u and the node v value is going to be less than or equals to max difference. And after that we have something like a query from u to query array, which is a 2D array, and we have given two nodes u and v, and we have to determine whether there exists a path between node u and v. If there exists a path between node u and v, it means yeah, the answer is true, else it's going to be returned false. So let's take the example and try how we can solve this problem. So so yeah, we have something like this problem. So let's see. So in this problem we have given a there are n equal to 4. It means that our graph has 4 nodes only, so n is going to be a 4. Yeah, and the nums array is given as a 2 comma 5 comma 6 comma 8, and max difference is going to be a 2. We can write it a difference, and we have something like queries. So let's see how we can solve this. So you can see firstly we have to make like a graph. So if we have something these are going to be undirected edge. So like if we have something like graph from a to b, if there is a edge from a to b, we can also say we can move from b to a also. So yeah, by undirected this it mean that. So let's see how we are going to. So the problem is to whether we have to say from if we can go from 0 to 1, or we can and second is like if we go from 0 to 2 or not. So how we can and in third third query it's a 1 comma 3 again, can we go from 1 to node 3. So like if we make something if we say we have a graph like this, something a graph of this. So if we find some graph, then any if two nodes for which we are calculating answer, for let's say we are solving the query for two nodes u and v, like it's a u and v. If both lie in the same graph, it means that it's going to always possible to move from one node to another, or vice versa from v to u and u to v. So so the problem you can see, if we do something like that, our answer is going to be very easy. Like we can simply check if u lies in this is component, and also v lie in same component. So it means that this graph will going to be divided into some different components. So let's say this is our one component, another component will look something like this. Graph has only two, and this has, let's say, assume this has only one. So the graph is going to be divided into different components, and we have to check whether we can reach any node from u to v in that component only. So let's say if we have something like u comma v, u lies in this component, v lies in this. So in that case, the answer is going to be false, because we can't move from one component to another, because components are not connected to each other. So yeah. So so what we can do, so if we was able to find a different component from this nums array, we have to make a graph. And if we make a graph with different components, we can easily answer the query. So after seeing this thing, you can if you have studied about disjoint set union, disjoint set union will immediately come into your mind. So if you have not studied about this, no problem, I will explain it in detail in this video. So yeah. So let's see, firstly let's see how we can make something how we can make array from like a no graph from this array. So so it looks something like 0 1 2 comma 3, and the value is going to be 2 5 6 comma 8. So this is going to be our like a value, and this is going to be our nodes. So these are our nodes, and these are is going to be our values. So because the values are arrays already in a sorted, so we have to don't do anything. So let's say if there is a path from 2 to 5, can there sorry, there is an edge from 2 to 5, like node 0 to 1, can is this possible? So like the value of nums of 0 is 2 and nums of 1 is 5. So the max difference between them is going to, like absolute difference between this is going to be 3. But you can see our difference can be only up to 2. So it means that there is no edge from no like this one this 2 and like node 0 and 1. So our graph will look something like this. For at as 0 it will look something like this, and for 1 it will look something like this 1. So now let's move to the next one. Can there is a edge, can there be edge between node 1 and the node 2? Yeah, we can say yeah, there can be an edge because the difference between them is their value is going to be 1. So let's assume there is an edge between this graph. So it like as there is undirected graph, so there is be no arrow in this. So like it's a two-way. If we don't draw array, it means like there is a two-way communication. Like we can go from 1 to 2 and 2 to 1. Yeah, there is a there is a edge. Now let's move to the second. Can there can be edge from 2 to 3? Yeah, you can select the difference is going to be a 2 only. Like 8, my absolute difference between 8 and 2 is 8 and 6 is 2. So there is a edge. So we can say our graph will look something like this. So now we can find like our first component looks something like this and the second look like this. So now to answer our queries, let's say what are the our different type of queries? 0 1 0 2 1 3. So first our first query is something like 0 comma 1. So like you can see 0 lies in in first group and 1 lies in different group, so it's not possible. So we have to return false for this, because like we can't go from one component to another component because component are disconnected. So another second query is like 0 to 2. Again 0 lies in first component, 2 lies in second component. For it's also going to be a false. Now for third one, like a 1 comma 3, 1 comma 3. So yeah, one lies in second component, three also lie in second component. So it's going to be a true. Similarly for 2 comma 3, 2 lies in second component and 3 also lies in second component. So it's going to be a true. So yeah, you can see like we get our answer. But how we can efficiently check like which node belong to like which node belong to which component? So let's say if we have n component and we have to traverse every component, like for every node we have to do this. So like an component, and for every node we have to track this thing. So it's going to be like queue no like queue into two nodes, because for like every query has two nodes. So it's going to be time complexity is going to queue into two into like overall n nodes, because a component like overall component has only n nodes. So it's going to be this like queue into n into 2. So but you can see like this in this problem the constraints are pretty high. Like these constraints are up to 10 raised to the power 5. So we can't do this because 10 raised to the power 5 into 10 into 2 into 10 raised to the power 5, it's like we can say it's 2 into 10 raised to the power 10, which is pretty high, which can't like which can pass in a 1 second. So yeah, so it's like a 2 into 10 raised to the power 10, sorry. So yeah, so we have to do like something better to solve this thing. So like if we have make this component, can we solve this query in a constant, or we can say like or log n? Like if we can solve this in a log n, it's going to be a this and this q into 2 become log n. So n into log n will work. So can we do this? So yeah, the same problem, like exactly same problem can we solve with DSU. DSU is only for to solve this kind of problem, to check like in this component what we have to check. We have to check whether this belong to same component or not. So DSU can help in this. So let's see how we can like now you know how we can solve this problem, but we have to only optimize this thing by using DSU. We can make different component and we can solve this. So let's see how we like what is DSU. DSU stand for Disjoint Set Union. Disjoint Set Union. So in this, what so in this problem, what we have to do, we have something in this problem, we are given something like some node, different nodes from 1 to n, or we can say 0 to n, something like that. 3, 4, 5, 5, 6, 7, and 8. We are given something like some nodes from 0 to n, or we can say 0 to 1 to n, or 0 to n minus 1. And we have given different types of queries, so you can merge something like 1 comma 2, or like 1 comma 2. You can merge 3 comma 4. You can, like, we have to merge this something like this, 5 comma 6, 8 comma 7, and say we have something like 3 comma 4, 3 comma, sorry, 3 comma 2, 3 comma 4 is already done, 3 comma 2, yeah. And we can say also 1 comma, we can say 5 comma 8. So we have different queries like that. So what happened in this, we maintain a simply a parent array. So what we have to do, the problem is like we have to merge an edges, or we can say and like this and queries. And after that we have to find the parent of that like child, like if the parent of both the nodes is going to be same, like if parent is going to be a same, it means that they belong to same component. It means that they belong to same component. So this is the main idea. So like if they belong to same component, same component, their parent is going to be same. So this is exactly problem we are solving. Like in this problem we have to do like same thing in this. So yeah, initially the every node's parent is going to be node itself only. So we have something like this. So now we have something like 1 comma 2. So we have node like 1 comma 2. So let's say we can make node 2 as a parent, node 2 as a child of 1. So the parent of node 2 is going to be 1. So it will look something like 1. So we can add here the node, parent of node 1, node 2 is 1. So again second query is like 3 comma 4. So again we can mark like node 4 is a child of node 3. So this is going to be a 3. Then we have some like similar like 5 comma 6. So 5 comma 6, 5 comma 6. So our like parent of 6 is going to become the 5. Then again we have comma 8 comma 7. So let's say in this the seventh node parent is going to be 8, something like that. So now we have everything up to this thing is okay. So now let's say we get something like 3 comma 2. So who is the parent of 3? Who is the parent of 3? Parent of 3 is 3. Who is the parent of 2? Parent of 2 is 1. So you can see parent of 3 is 3 and the parent of 2 is 1. So now we have to combine this, like so our tree looks something like this and this look like something like this. So we have to combine this thing. So how we can combine? So we can make a new something like 3 is a child of 1. So it will look something like this. So this 2 will remain same, and this, so now our tree looks something like this. And after that, who is the parent of 3? 3's parent is 1. So we will change this value to 1, we can say. Yeah. Now again we are curious something like 5 comma 8. So parent of 5 is we can say 5. You can see parent of 5 is 5. Parent of 8 is 8. So yeah, so it's going to be 5 comma 6 comma 8 comma sorry, 8 and a 7. So our like tree will look like something like that, and the parent of 8 is going to be a 5. So we can change this value to 5. So like if we make something a parent like this, now we can query anything. Like if we have to check that the two node belong to a same component, like if the parent of the nodes are same for like 1 2 3 and 4, their ultimate parent is going to be 1. So but you can see like for 4 the parent is going to be 3, but in actual the parent of these all node is going to be 1. But if we if we find something like ultimate parent, so in this the like the array which we get, the parent array is not going to be ultimate parent array, it's going to be simply a next parent, we can say next parent, or maybe ultimate parent, but not the ultimate in case of everyone. So in this the 4, the its ultimate parent is going to be 1, but in this parent array it's going to be 3. So we can do something like it's a simple like recursive thing. We have to move we have to move up until we get the ultimate parent. How we check like we reach the ultimate parent? In the case of ultimate parent, the parent of that node is equal to the node value. Like you can say in this one, the node value is going to be 1 and a parent value is going also going to 1. Similarly in case of 5, you can see the value is 5 and the ultimate like parent is 5 and the value is 5, so it means that it is also ultimate node. So in this case, after like finding the ultimate, it will look something like 1, and for this also it look like 5. So it means that we get two disconnected component like this and this. So now we can simply query like everything like so let's say we have got query like 3 comma 4. So we have to check whether they are uh, belonging to a same component or not. So we check who is the parent of 3. Parent of 3 is 1, and who is the like sorry, not parent, the ultimate parent. Ultimate parent is 1, and who is the parent ultimate parent of 4? It also going to 1. So if the this value matches, it means that they belong to same component, else they belong to different component. So let's try for node 1 and comma 4. Oh sorry, node 1 and the 5. Or we yeah. So node 1 parent is ultimate parent is 1, node 5 ultimate parent is 5. So like this value are not equal, so it means that they belong to different component. So yeah. So but if we do some like how we are like merging this thing, like we are merging this tree, because in actual code we are writing, we are not making maintaining this tree, we are only maintaining this parent array. So how we are going to merge something like if we have 1 2 and we have to 3 4. So we can simply mark the like we can find a ultimate parent of this component and ultimate parent of this component, and then going to merge with or left with the right, or left or right with the left, so that's not a problem. So in this like if we get something tree like something like that, 1 comma 2 comma 3 comma 4 comma 4 and 5, like node 4 5. So if we get something like tree this like this, if we have to query like check 5 comma 4, it's going to be like, and like time complexity is going to be again going to be n. So we have to do it in some better way. So like in this DSU we have two optimization. First optimization is known as a path compression. And second one is like a union by path, or like whenever we have to do union of this like node. By union I mean like we have to check make a query like 3 4 belong to a same component, so we have to do something like that union. By union I mean that there are in union we have to something like first one is by depth of the tree, and the second in was like a size of the tree. So if we do any of these optimization, that time complexity will reduce to big of like log n in this case. And also if we do like this optimization, it's going to be a big O of log n. For every query we have to find for like find parent like that. So but if we do this thing like path compression and the union, the time complexity is going to be a like big O of yeah, we can say big O of alpha in this case. And this alpha is very low, like big O in worst it's going in average, it's going to be a big of 4 operation, only 4 operation for finding. So at the end it is going to be a, we can say it is a almost a constant time operation. So if we do this optimization, then it's going to be a constant operation only. So let's see how we can do make this optimization. So first is like by like this path compression will I explain while I writing the code, and this will I easily explain now. So let's see what is the like merging thing look like. So let's say we have something like this two like 1 2 3 this is a yeah, this is something a tree, and second tree is something like this. Let's say it's a 12, 13, 14, and something like 15. So like if we have like these are two these are two components, and let's say we have something like we have to make union of 2 comma 15. So like 2 comma 15 are connected, so it means that these are going to be connected. So there are two ways. Either we can make this component a child of B, or component B a child of A. So if we do something like component A child of B, so our graph will look something like this: 1, 2, 3, 4, and it will look something like 12, 13, 14, and 15. So in this you can see the our overall height of the our overall height of the tree is going to be a 4 only. In this case it was 4, in this case it was 3. So overall our height will remain same if we merge a smaller height tree with the larger height tree. So but if we do reverse something like that, like if we have something like 12, 13, 14, and 15, it's a 15, and if we merge like a larger tree, it will look something like 1, 2, 3, and 4. So you can see now our height overall height will increase by 1. So overall height will increase by 1, so it become 5. So you can see like whenever like if we merge a smaller tree with a larger tree, our height will remain as a larger tree's height. But if we merge a larger tree with a smaller tree height, then our height will increase by 1. So like if our height will increase by 1 every time if we merge a smaller greater with a smaller, then we can say in a worst case our we have to move like traverse big of an iteration only. So by doing this optimization, like merging a smaller tree to a smaller to a larger tree, our time complexity will reduce by a come off to a big of n. So you can see like why it reduces due to this reason, because we are our height will remain like a same only whenever we do this thing. So now so let's now understand like path compression only now. So what is path compression? So in path compression what happen is, let's say if we have if we have tree look something like this: 1, 2, 3, 4, 5, 6. So this is the ultimate ultimate tree, like we can say parent array we get, and from parent array this is tree look something like that. So like if we have to calculate the ultimate parent of 6, so who is the ultimate, how we can calculate the ultimate parent of 6? So from 6 we can go to 5. From 5 we can go to 4. From 4 we can go to 3. From 3 we can go to 2, and from 2 we can go to 1. So in our parent array, parent of 6 will look something like 1 after doing this finding the ultimate parent. But you can see like if we are finding the ultimate parent of 6 in like while calculating that, we also find the parent of 5, 4, 2, 1. So instead of only making this thing parent of 6 equal to 1, we can, like if we are doing recursion for this, so we can also mark parent of 5 is going to be directly to 1, parent of 4 is also going to be a 1. So by doing this optimization, we like in first thing you can see like we have to do like 5 iteration. If we have something like 100 length, we can say tree we have to do 100 iteration, but these iterations can be only done once, and after that this is going to be constant time operation, because like we don't have to even do one iteration, we have to only do check. So it's going to be constant. So overall by doing this technique, overall it's going to be a constant time complexity by doing like a path compression and a union by depth or union by size. So so I only explain the union by, we can say, depth, but you can also do union by size. In size we are maintaining the size of the tree. So let's see how we can do. So yeah, this is the main thing. So let's see the code for this thing, how we can do thing like how we can solve that problem. So So firstly, so let's see the code for firstly see the disjoint set union code. So this is the init function. It's so we are maintaining the depth and the parent array, and I initialize the int as a like a large maximum value that is possible. So in init array, what happen? I am making the parent of like for ith node the parent is going to be I, but only doing that thing. So how we am so let's see how we are using union. So for union two node u and v. So let's see if where is that code? Uh, so yeah, like here. So like if we have to do something like 3 comma 4 belong to a same component, so we do union. So for that we are going to what was we doing? We are going to find the ultimate like parent. We can say ultimate parent, and then we have to do mark that like combine a we are going to combine a like a like smaller tree with the larger tree. Yeah. So let's see like we have u and v get to node, we have to do union of that. So we find the parent of u and find the parent of v. So like if the if the parent of both the node are same, it means that they already belong to same component. So we are going to we can simply return this function. So we do nothing. So now we get that like if the values are not like they belong to different component, we check if the depth of the u like the depth of u tree is greater than the depth of v component, we can say component or simply tree, then we are assigning the parent. Like we are assigning, you can see a max depth of u v is parent of v is going to be u. So the we are combining the minimum tree with the maximum tree, you can see like parent of v is going to be a u because u is the u tree has a greater height. Similarly the this is the reverse case, and if the bot tree has same height like so yeah I think I skipped this case. So like if the bot tree has same height something like that, we have something like 1 comma 2 and 2 comma 5. So how we are going to combine, because in this case if we combine a with the b or b with a, the overall height will increase by 1. So we are simply doing this. So we are combining a v node component, a v node tree with a u node, and increasing the height of the u. So that's it. So yeah, this is a very simple thing. So like how we are going finding the ultimate parent. So I am checking like if the parent of node equal to node. So like if the parent node value is going to be node, it means that it is the ultimate parent. In that case I am returning node. As what I am doing, I am calling the same recursion function for parent of node. So like let's say we have something like a tree like this, and we are finding the parent of 2. So we move to 1. So we check, like you can see we are checking if the value are same. If the value are not same, we are calling this function with a parent of 1. Parent of 2, parent of 2 is going to 1, again we are going to calling it for 2. So like sorry, this is going to be a 4. So again 4, so 4 is the parent, like for this node 4 is the ultimate parent also. So yeah, in that case I am returning. But you can see we are doing something like something here, like every node like for 1 2, every node we have visited in this, we are marking the ultimate parent at their parent. So we updating the parent array with their ultimate parent. So we have to don't do calculation for every like every time we have to for the same thing. Like so like if we have traversed something like 3 2 1 4, so if we get calculated for answer 2, again we get query for 1, so we can answer this query in constant time. So let's see now how we solve this problem using this thing. So in this firstly I am maintaining a tr like a t array which have a value and we can say I, but I think we can simply skip this also, because the array is already going to be sorted. Because I while solving that problem I think that array was not sorted, so for that case I maintain this. So that because when the array gets sorted we are calculating the answer basis of on these things, but we have to find the actual value from where the like where this node 0 lies, where that node 1 lies. So for that I have done this thing, but in this case the array is sorted, we can simply get that thing easily. So I am maintaining the vi value and the index value, and after that I am calling init function, then I am sorting this array so that I am getting the sorted by v of I value. We don't need even to do sort the array. So let me comment this thing. So we can yeah, so after that I am simply do union, like checking whether like I am traversing from 0 and tell I am checking up to n minus 1 size. So I am checking like if the difference between like absolute difference between the first node like this value 1 and 1 and 3 is going to be a less than equal to max difference, it means that they belong to a same component, then we have to do union. So in that case I am calling this union function with like a dp like t of I comma 1 and t of I comma like I plus 1 value. Yeah, so after that we get our parent array. So how we can get like solving this query? So like, so we are checking like who is the what is the value for 0th node and what is the value for v node. So after finding that value, we are checking if this value belong to the same component or like a same component. So like we are finding the parent of u and the parent of v. If the parent of both these nodes are going to be same, it means that they belong to same component. Then we are adding our true to our answer, like because we have to return a vector of boolean answer for every query, like whether it's a true or false. So we are adding true in that case, and if the values are not same, we are adding false. So yeah, that's it for this video. I hope you understand the DSU topic. So yeah, you can like solve a lot of different problem based on this DSU concept, and it's a pretty standard. We can say pretty standard graph algorithm. We can say. So yeah, thanks for watching this video. I hope you like this video. If you like this video, please like and subscribe my channel. So I will try to make more topic videos on the advanced topic of graphs and other thing.